The fundamental task of a nerve cell is to receive, conduct, and transmit signals. Neurons propagate signals in the form of action potentials, which can travel great distances along an axon without weakening. To transmit an action potential over such a distance without weakening requires that the signal is continuously reamplified along the way. The central molecular players in this process are the voltage-gated sodium channels, which undergo a cycle of finely choreographed conformational changes. When an action potential passes, sodium channels open in response to membrane depolarization. Sodium ions rush into the axon, further depolarizing its membrane. Within a fraction of a thousandth of a second, however, the sodium channels switch to a new inactivated state, in which they are closed, but now also refractory to reopening. In this way, the membrane potential can recover quickly after an action potential has passed. The sodium channels then reconvert to the closed state, ready to be opened again when the next action potential is encountered. Let's examine the changing state of the sodium channel during an action potential. When no stimulus is present, the sodium channels remain closed, and the electrical potential measured across the membrane remains constant. However, if a depolarizing stimulus is applied by a brief pulse of electric current, the membrane will start to depolarize, away from the resting potential of about -80 millivolts. Some of the sodium channels will open, permitting sodium ions to enter the axon along their concentration gradient. If the depolarization is sufficient, even more sodium channels open, and the membrane potential rapidly approaches the equilibrium potential for sodium, about +40 millivolts. At this point, the sodium channels close, adopting the inactive conformation, where the channel is unable to open again even though the membrane potential is still depolarized. The sodium channels will remain in this inactivated state until a few milliseconds after the membrane potential returns to its initial negative value. The action potential is propagated along the length of the axon in only one direction. By examining the membrane potential and state of the sodium channels along a length of the axon, we can see why this is so. As a depolarizing stimulus reaches our section of the membrane, sodium channels open and current flows into the axon. This in turn depolarizes adjacent sections of the membrane, causing adjacent sodium channels to open, and the action potential is thus propagated along the axon. Sodium channel inactivation prevents the depolarization from spreading backward along the axon.